We're now going to look at the second derivative test, and I have it laid out here. This is, I think, a nice way of stating the test so that you can see what's going on here. So you're going to let x equals c be a critical point of f of x. So this is a way of determining whether a critical point of a function is a min or a max. So you can use the first derivative test, but if this test applies, this is actually a lot easier to do. Okay? So in order for it to work, the second derivative needs to be continuous on an open interval containing c. So that would mean the second derivative would actually have to exist at c as well. So this has to be a critical point where the derivative is equal to 0, okay, and where the first derivative is equal to 0 and the second derivative exists. And so if the second derivative is continuous and on an open interval, then it must be either positive, negative, or 0. So let's just think about it. If it's positive, that means the graph is concave up, right? And if it's concave up, then the c has to be, the critical point has to be relative min, okay? Now, if the second derivative is negative, it means the graph is concave down, and that would mean the critical point would have to be a relative max. And then finally, it could be that the second derivative is 0. So in this case, the test is inconclusive, and you need to actually go and you go back and use the first derivative test, okay, to determine whether or not there is a relative min or max. Okay, so if it's positive or negative, the second derivative test is going to tell you what the critical point is, whether it's a min or a max. But if it's 0, it's inconclusive, and you have to use the first derivative test. So let's use it. I have a couple polynomial functions, so let's use it to, we're just going to determine relative min or max in this case. So I'm going to find the critical points by taking the derivative. So this would be 4x cubed minus 6x squared. Okay? And so now I'm going to set this equal, set the derivative equal to 0. Okay, and I can factor out a 2x squared, it looks like, and I'm left with 2x minus 6. And that's equal to, 2x minus 3, sorry. I factored out the 2x, and that's equal 2x squared. That's equal to 0 here. So, so either x has to equal 0, or in this case, x has to equal 3/2. So these would be the two critical points of this function. Okay, now the derivative here is a cubic, and so it actually has 3 zeros, but this is a 0 with multiplicity 2, right? So this 0 actually has a multiplicity 2, and then you have 3/2. And so what the second derivative test says, is if the second derivative at each of these points, if the second derivative is positive, it's a min. If it's negative, it's a max. So it's really nice and easy to do because you don't have to set up the whole table like you do for the first derivative. Okay? You just have to evaluate the second derivative. So what I'm going to do here is I'm going to set up this, or I'm going to take the second derivative first of all. So this would be 12x squared, and then this would be minus 6x. Okay, so 12x squared minus, and you know what? It would be minus 12x, sorry. That's kind of running into things. So I'll write it down again. So 12x squared minus 12x. And so now I just have to evaluate the derivative at each point. So at f equals 0, look, I'm going to plug it in, and I get 0. So it's inconclusive. So at this point, at x equals 0, it's inconclusive. But if I plug it in at 3/2, then I can plug in 3/2 there. I'm going to do that on my calculator. Or maybe I'll do 12 3/2 squared minus 12 3/2. Well, I'm going to go ahead and plug it in. 12 times 3/2 squared minus 12 times 3/2. And I get 9 here. So that means it's positive. The derivative is positive, and so x equals 2/3 here. X equals, 3/2 is a relative min. Because the second derivative is positive. Now, for the 0, that's inconclusive. So what I need to do is I need to do a second derivative test. I need to go back. I need to do the first derivative test. So, but I just have to do it for that one point here. So this is where x is equal to 0, and then 0, positive infinity. So I'll put in a -1 here. And so what I'm going to do is I'm going to place this into the first derivative. So this would just be 4 minus, put in -1. So this would be 4 minus 6, and I would get -2. So f of -1 is equal to -2. And so this is negative, the first derivative. And then I'll put in a positive 1 here. And again, this would be, oh, by the way, if I need to place it in here, and if I place in -1, this is -4 minus 6, which is -10, but it's still negative, okay? And if I put in it at 1, this would be a positive 4 minus 6, which is, again, -2. So it's still negative. So what that means is it's neither. X equals 0 is neither a min or a max. Okay? So in this case, the second derivative test very easily and quickly tells us that this is a relative minimum, and you don't have to set up a table or anything. You just take the derivative again, find when the derivative is equal to 0, then you take the derivative again, evaluate it, and if it's negative, or if it's positive, it's a min. If it's negative, it's a max. Very, very nice test. But it didn't work on here because it was 0 at that point, and so the test was inconclusive. So I did have to use the first derivative test. So let's actually plug in our original function, which is x to the 4th minus 2x cubed, and we'll do it at a standard window. And it looks like we get this thing that actually comes down, flattens out, and comes down again and goes back up. And so maybe I'll zoom in on that center. And so we see that critical point is a 0. The derivative is 0. It's a horizontal tangent, but it's neither a min or a max. It was negative this way, and then it goes back to being negative that way, as opposed to positive. So that's neither a min or a max. Now this one over here should be the 3/2. That's the relative min. Oops. So, oops, sorry. 3/2. And there you go. There you have the relative min. Okay, very good. That is the second derivative, at least this part is the second derivative test, but in this example it's inconclusive, and so it was neither a min or a max. Okay, well let's try one more polynomial. Now it's a fifth degree. So let's find the critical points here. So take the derivative, and I get 5x to the fourth minus, it looks like 20x cubed. Okay, now I'm going to set that equal to 0. This is equal to 0. And now I'm going to pull out the, it looks like I can pull out a 5x cubed, can't I? And when I do that, I'm going to get just x minus 4 is equal to 0. So again, I get x equals 0 as a critical point, and then I get x equals 4 as a critical point. And you can see that this one has a multiplicity of 3. In this case, because it comes from the x cubed. So in other words, the fourth degree polynomial should have 4 zeros, and it does. It has 3 zeros of 0, or 3 roots of 0, and then that root of 4. Okay, well, my guess, well, let's take the second derivative here. So the second derivative is going to be 20x cubed minus 60x squared. And so, like before, f double prime of 0 is equal to 0, so it's inconclusive for that. So what about f double prime of 4? I think it's going to be conclusive for this, so let's check it out. So I'm going to plug in 20. So I'm plugging this in to the second derivative. So it'll be 20 times 4 cubed minus 60 times 4 squared. Oh, I hit graph. Hit return. And what I get here is I'll write it here, 4 cubed minus 60 times 4 squared. And what I got was 320. So it's positive. So being positive, it's concave down, and x equals 4 is a relative min. Again. So we got a relative min at x equals 4. It's inconclusive for 0, so I'm going to have to do another test here. Negative infinity to 0. Zero to infinity. This is at x equals 0. So I can plug in the test points, -1 and 1 again. And when I plug in -1, I get negative 20 minus 60. Oh, but I'm putting these in the first derivative. I got to be careful, because I'm doing like a first derivative test. Wait a minute here. Yeah, I'm doing the first derivative test here on this. So putting in -1 there just gives me 5. Putting in a -1 here would make that like -20, but minus, so that would be 25. So this would be positive. And then if I put in a positive 1, I would get a 1 here minus a 1 there. And so this would be -15. So this is negative. So this is going from positive to negative, the original function. So x equals 0. The first derivative test was inconclusive. I'm sorry, the second derivative test is inconclusive. So we did the first derivative test, and we got that x equals 0 is a relative max. Is what I find out. So let's see if I did this right. You gotta keep things straight here. You gotta really be careful. You gotta remember, for the first derivative test here, I gotta plug it in the first derivative. For second derivative test, plug it in the second derivative. But if I'm using the first derivative test for an inflection point, I plug it in the second derivative. That's what was confusing me, I think. Okay. Let's graph this. But I'm not bringing it in. We do see it 0 there. Let me actually go to standard window. Hopefully get a more full picture. Okay, so this looks like here at 4, this would be at 4, that does look like a relative min, and that does look like a relative max. So let me hit my window here, and I'm going to have to change this to like probably -50. That might give it to me. So you're going up. Oh, it still doesn't give it to me. Okay, I'm going to change my window again then. And we'll change this to -100. Oops. Ooh, it still doesn't give it to me. That goes way down at 4, doesn't it? Oh, it goes down to, actually, oh no, that's the second derivative. So let me do my window one more time. See if I can get it. -500. There we go. And then I can see that that min occurs when at 4 here. So plug in 4, and we see that's the min, and it's -256. Okay, is that min? So there's at 0 it's a relative max because it turns around, and then at 4 it's a relative min. And the 4 we were able to use the second derivative test, which is a lot easier because it's easy to take the derivative usually and then you just evaluate it. You don't have to build a table and then evaluate it at multiple points. So the second derivative test is nice when it works, and if it doesn't, you just use the first derivative test. Also notice the reason I did these two is the first one, they both had an inconclusive critical point. Right? The second derivative test was inconclusive for this one, and then when I did the first derivative test, I saw it was neither a min or a max, and in this one, it was inconclusive, but when I did the first derivative test, I saw that it was a max. So just because it's inconclusive doesn't mean that there's neither, if it's 0, it doesn't mean that there's neither a min or a max. It means that the second derivative test is not conclusive. It's not going to give you what you want. You have to use the first derivative test, and in that case, there could be a min or a max, or there might not be. Just depends on the critical point.